All right, so it's the last seminar of the quarter. We're happy to have Nathan Benjamin visiting from nearby USC, and he'll tell us about universality and spin-refined data and higher dimensional CFTs.
Okay, thanks very much, Theo. Thanks for inviting me, and I'm very, very happy to be here. So this work that I say will be based off of some collaboration with Jay Hadley, Shurda Pal, Davidson and Stefan, and Ishin Shu. So let me start with just a big picture question that I'm going to ask in this talk. So the question I'll ask is, what features of CFTs are universal? So what are universal features that all conformal field theories share? So this is the question that I'll address today. And this is kind of like a famous and old question. And in fact, if you just poll a random person, like if you go to a random coffee shop, if you poll a random person this question, they'll probably tell you the Carty formula. They'll probably say the Carty formula is the most famous universal feature that all CFTs share. So just as a reminder that in D equals 2, this question is well known. And it's well known that for all compact 2D CFTs, we've known, thanks to Carty, that the entropy of high energy states in the CFT is universal. So it doesn't matter the details of the CFT, the functional form is, it doesn't matter if it's, what any of the light states are, but the functional form of the entropy at large energy is completely universal and is just determined by a single number, which is the central charge. So the density of states is given by some expression like this as a function of the conformal dimension and the spin. And as long as the twist, delta minus J, is much bigger than the central charge, C, then the entropy of conformal field theories is always universal. It always takes this functional form. Okay, so this is true for all CFTs. It's true for holographic theories. It's true for the Eisen model. It's true for whatever. It's teacher card. And okay, so this is universal, and is determined by a single number. So of course, this number C has other interpretations in 2D. It shows up in the TTOBE. It's related to some Casimir energy when you put the theory on a cylinder, things like this. But in this talk, I'm just going to use this as just a parameter, a positive real number, which is some parameter of the theory. And of course, the derivation that we're all taught comes from modular invariance. Which is simply the statement that if you define the torus partition function as a function of some inverse temperature beta and some chemical potential omega, so this is your trace of your Hilbert space of just the usual partition function from Statlek. This thing is invariant under some non-trivial SL2Z action. And the reason is you can view this as a path integral over the torus, and the torus has a non-trivial diffeomorphism, a large diffeomorphism to SL2Z. So there's an SL2Z action on some variable tau, which is related to the chemical potentials. And at very low temperature, there's some universality coming from the vacuum. At low temperatures, there's the vacuum has some Casimir energy, which is related to this parameter C. And then you do an S transformation, which is an element of SL2Z, which roughly takes this temperature to 1 over the temperature. And this gives you that the partition function up to all orders in perturbation theory in beta takes this form. And of course, taking the inverse Laplace transform of this guy just gives you the Carty formula. Just going from basically canonical ensemble to microcanonical ensemble. So hopefully this is all review and straightforward. This tells you this entropy of states for 2D CFTs. Let's stick in 2D for just 1 second, despite the title of D bigger than 2. You can also ask questions about, are there universal formulas for more refined spin quantities? So here, I'm computing the partition function weighted by some chemical potential, and I'm imagining omega is an order 1 number, so that beta omega is still very, very small. And you can ask, what if I make beta omega a large number instead? So for example, just as an example, you could also ask this question. What if I were interested in computing the same partition function, but with some -1 to the j? So I treat even spins with the +1 and odd spins with the -1. So this is not the -1 to the f operation. This is not like a Witten index or something. This is -1 to the j. It's like a square root of the square root of -1 to the f. And then the question is, what does this look like at high temperatures? And again, omega over 1. Now, naively, you might say, oh, if I know this, I know this. Because naively, you would say, if I just take this expression, and I said omega goes to omega plus pi over beta. Right, and I said this expression and said omega to pi over beta, I precisely recovered this. Right, because this pi over beta, the betas cancel, and I just get e to the I pi j, which is just a -1 to the j. So naively, you might think that some expression like this is enough to get this. But the answer is no. Just from this expression alone, you're not going to get this expression with a -1 to the j, and it's because with this new value of omega, the omega is no longer order 1. And essentially doing if you try to do the saddle point approximation, you'll be outside the regime of validity. Another equivalent way of saying this is that with this value of omega, the real part of tau is very close to a half, and if you do an S transformation of that, you're not going to get a vacuum dominance that you can just see very explicitly. Okay, so if you'll understand the question I'm asking. Okay, so you might think that this is hopeless, but in fact the group you have to work with is not just the S transform. You have an entire SL2Z's worth of transform, and there's a more non-trivial element of SL2Z that'll tell you what this quantity is. And if you work it out, if you look at this element of SL2Z, so this is a 2x2 matrix with integer elements and the determinant 1. And just a reminder, this element takes tau goes to tau over 2 tau minus 1. Minus here. If you look at this element of SL2Z, you'll see that this one will do the trick, right? Because the real part of tau is very close to 1/2. Now there's a 2 tau minus 1 in the denominator, so again you'll map it to some you'll map the vacuum to some high temperature term here. So you can play the exact same game, and then you can do this more complicated modular transformation, and you can get the expression for this new partition function in this limit. And the answer you get, it's okay if I write down here. Here. Or people,
Yeah.
people can see down here. Yes. Okay. The answer you'll get is a very similar expression. The only difference is that in the exponential you're down by a factor of 1/4. So this -1 to the j, it takes the exact same functional form, but you're down by a factor of 1/4 in the exponential. So actually you're down by a lot because it's in the exponential, and it is at high temperature, and it's saying that almost all the even and odd states cancel each other, even and odd spin states cancel each other, and you get this precise expression for what the partition is. And you can also play this game more generally for any bosonic 2D CFT, and you can compute an arbitrary phase. And you can play the exact same game. So suppose you have some rational angle P over Q, and you insert this into the partition function. You can ask, what's this partition function, where you now kind of discriminate on spins mod Q. And well, now you use a more complicated element of SL2Z. You'll need to use one where there's Q and minus P here, and there's some elements here. And the answer you'll get is the exact same thing, except now this 1/4 becomes 1 over Q squared. And interestingly, it's P independent. Okay, so what is this? What is this? And this is now we need you need beta Q to be much less than 1, not just beta T much less than 1. So what this tells you is that suppose someone were to tell you the partition function at high temperature, you know what the answer is. You actually know the partition function at all rational angles. So at any rational angle, you know what the answer is. You just multiply by 1 over q squared in the denominator here. And we derive this all just using modular invariance in 2 dimensions. So of course, modular invariance is very special in 2 dimensions. That's the only time where there's an S1 times S1, and you can interchange the S1s and play various games. And the question I'll ask in this talk is something like this true for d bigger than 2 CFTs? So for d bigger than 2 CFTs, if I compute the partition function at some finite temperature, can I also tell you this more refined, spin refined information, like the partition function with a -1 to the j, or maybe some more complicated function of the spins? And of course, for higher DCFTs, there could be, if you're in 4 or more dimensions, there could be multiple spins you could turn on as well, multiple ones with the Cartan of SOD. So this is the question we'll ask, and well, the answer is going to be yes. Even though we don't have modular invariance, of course, but I'll describe using some effective field theory techniques how we can get this question, and I'll even tell you what the answer is, like kind of the punchline. So if you fall asleep, maybe you won't understand, you won't see the derivation, but at least you'll know the answer, and you can tell your friends at parties. The answer is that in the log of the partition function, so in the free energy with this angle inserted, you're down by a factor of 1 over q to the d. Okay, so to leading order in the high temperature, you're down by a factor of 1 over q to the d. So of course we see in 2 dimensions, you're down by a factor of, well, -1 to the j, you're down by a factor of 1/4. So that'll become 1 over 2 to the d for general dimensional CFT. Or for a general rational angle, you'll be down by a factor of 1 over q to the d, which generalizes the 1 over q squared.
On the make over on this side, what is it giving you exactly when you do the?
Oh, very good question. Yeah, good. If you take the inverse Laplace transform, that's a good question. It's a little bit subtle to define these inverse Laplace transforms when you have something like a -1 to the j, because if you were just to like do the inverse Laplace transform, write the saddle, and just trust your nose, you'll get something like something like sum over j -1 to the j, where you need to smear this j a little. So whenever you do these inverse Laplace transforms, you need to smear a little bit in both delta and in j. The proper way to define this, I guess Jungji is in the audience, he's like an expert on this. The proper way to define this is with precisely saying how much you need to smear by, and this is something called Tauberian theory, probably you know about. And it's very, very subtle to define these with betas -1 to the j. So in the canonical, like in this picture, in the canonical ensemble, this is all completely well defined. Like this is a well-defined function of beta and omega. I can take the limit as beta goes to 0 and then omega some fixed number. So this is always a well-defined statement. If you want to interpret this in some microcanonical, then I think it's very subtle, because it depends on when you smear, is the final spin that you include even or odd. So like very heuristically speaking, you would be saying that -1 to the j smeared over j will give this guy where you're down by a factor of 1 over 4 here. But to make this really precise, like I think my understanding is this Tauberian techniques cannot really do that, but it's a very good. Any other questions? Okay, so this is where we're going to go. So this is the motivation and the question we're going to ask. Let's have a race over here. Okay, so now let's work in higher dimensions. Well, in general dimensions, it can also be 2. And let's try to compute this quantity. And we're going to do this. This is this is a partition function, and you can evaluate this by doing some path integral on this geometry S1 times SD minus 1. Where this geometry now, this S1 is a circle of length beta. So this is like some thermal partition function. And to implement this twist, what that means is that as you go around the S1, the SD minus 1, you twist by beta omega. So where when you go around S1 single circle, twist by beta omega. So to be more explicit, then I have these coordinates theta and tau, where theta are the angles on the SD minus 1. There could be many of them. There could be like d over 2 of them, and tau is the coordinate on the S1. there's identification of this form. And the key idea, or the key assumption we'll be making, is that we're going to take the beta goes to 0 limit of this theory, and we're going to write down an effective theory. For the d-1 dimensional theory. And we're going to assume that generically, we have some d-1 dimensional quantum field theory. There's no parameters to assume because the d-dimensional theory is a conformal field theory. So there's nothing we can assume. So we're going to assume that this d-1 dimensional theory is a gapped theory. So this is an assumption. Of course, sometimes there are symmetries protecting it. For example, if it's a free theory, you'll still get a free theory in one lower dimension. Or if it's a supersymmetric theory and you gap it with the appropriate boundary conditions with this -1 to the f for the thermal circle, then you'll also get a gapless theory. But generically, we're going to assume that this is a gap theory. So I mean that this is that in the d-1 dimensional theory, we're going to assume that the 2-point function of two operators is going to follow exponentially with some correlationally length c, which is going to be just proportional to beta. And what we're going to do is we're going to couple the original CFT to some background metric, and we're going to write the gap theory as a function of the background field. So because this geometry is a circle, has a circle vibration, we can always put this metric includes a Klein form. So this metric, where now lowercase indices go from 1 to d-1. Now another a d-1 dimensional metric, a gauge field in a dilettante. We're going to say that this CFT as a function of this metric G is the gap theory as a function of the metric, the gauge field in a dilettante. And we're going to assume that this takes the form of some effective action, that is some of the local powder terms, which are a function of the metric, the gauge field in this dilettante. Now, the key thing we're going to use, where we're going to kind of make our money, is that not every term you can write down in this effective action goes. So the symmetries of your original CFT highly constrain the terms that show up here. So in particular, violent variance of your original CFT forces only a particular combination of the metric and the dilettante to appear. So if we define g hat to be e to the minus pi times g, you can only have a function of g hat. Otherwise, you'll have terms that don't respect the violent variance. And similarly, as is usual in this exclusive Klein reduction, d-dimensional coordinate invariance will give me d-1 dimensional coordinate invariance and gauge invariance of my theory. So the most general form of the thermal effective action I can write down looks like this. So there are infinitely many terms I can write down, but I'm going to organize them in a derivative expansion. Because just from dimensional analysis, you see, the more derivatives that you put into this thermal effective action, the more powers of beta you get. So you're going to be down by powers of beta. So there's some infinite expansion, and I'll write down the first few terms of this expansion. So the first term is some cosmological constant in my thermal effective action. And I'll just, for convention, I put a minus sign here, because this f will turn out to be positive. Then I can write down some Einstein terms, Maxwell term, and so on. So these terms, okay, this has no derivative, so this has no powers of beta with it. These two terms goes as two derivatives. So to make up the units, they have two powers of beta, and so on. So if you're interested in up to the terms including beta to the fourth, then you have to write down f to the fourth, r squared, and then maybe various other, r times f, and there may be various contractions. But if you're just interested in some finite order in the derivative expansion, there's only a finite number of terms you can write down in your effective action. And so here, f, c1, c2, etc., and there are infinitely many of these. These are some Wilson coefficients These are CFT dependent Wilson coefficients. And these are not necessarily universal. So these guys, FC1, C2, they will play the role of the central charge C from the 2D. I don't mean they play the role of the central charge C in that they control like the OPE or stress sensors or something, Casimir energy, something like this. But I'll just treat them as some real numbers that are parameters of the CFT. And a priori, you don't know what they are. You know how to compute them. The very nice thing about this is that these are defined for the CFT. Then you can put the CFT on any geometry that you want, and you just compute these geometrical quantities of this object, and then the partition function on this geometry will just be determined by the exact same unknown parameters. So here we can compute the CFT on any S1 times MD minus 1 with this. And in this talk, I'll set this MD minus 1 to be the sphere. SD minus 1. This way, we'll then compute the partition function that we design, this guy right here.
Nathan?
Yeah.
Are Chern-Simons terms
Oh,
ruled out?
very good question. No, very good question. Very good question. So these Chern-Simons terms will be present if the theory is in like even dimensions and has a gravitational anomaly. So for example, in 2 dimensions, if the C left minus C right is not, yeah, very good question. So if the theory doesn't have gravitational anomaly, it will not have these. In 2 dimensions, for example, if C left minus C right is over 24 is K, then there'll be some K times some integral of A. Or in 6 dimensions, there'll be some similar term. Yeah, that's right. Yeah, these terms are interesting. I'll discuss them a little bit actually at the end of the talk when we talk about this minus 1 to the chain. It's a very good question. Okay, so from this we can just now take any geometry we want and just compute them. So now this is just a problem in geometry, and for the case of the sphere, this is the answer you get. So the MD minus 1 is this SD minus 1. This is the answer you get for your thermal effective action. So the details don't matter, but I want to write this out just because there's some things that are interesting and universal. So again, it's going to be some infinite expansion in beta. And so I'll write the first 2 terms in this infinite expansion. And the actual coefficients don't particularly matter, but I'll still write them anyway, just because. Okay, so from this, here, this F, C1, and C2, these are again the unknown parameters of my theory. So here are 3 unknown parameters of the theory. I put dots on dots, there are infinitely many in here. But if you're just interested in, let's say, the first 2 terms in the perturbation theory so this S is roughly the log of the partition function, the free energy. So up to minus. So the leading order term is this term right here. Then there's a correction here, and there's an infinite series of perturbative corrections. From this, we can get the partition function, and we can also take the inverse Laplace transform, and we'll get the density of states or the entropy. So maybe I'll just write the first term in the entropy. So this is you can write the full expression. So for example, in 3 dimensions, if the CFT is in 3 dimensions, the entropy. So this is the analog of Carty's formula. This is the leading term, and there's an infinite series of questions. And I should also say that this leading term also appeared in a very nice paper by Edgar Shigulian around sometime. I forget exactly when. Again, here there's this first parameter f, but in these higher correction terms, the C1 and C2 appear. Like for example, there's a term that's like 32 C2 over 3 delta squared minus j squared. So if you're interested in higher orders in perturbation theory, these are present. You can ask what the regime of validity of this entropy formula is, and the way we do this is we just take, when we do this inverse Laplace transform, we do it by saddle, and you need the saddle to be at beta very small. Otherwise, you don't trust this effective field theory computation. And when the dust settles, that means that you need your twist delta minus j to be much bigger than square root of f times delta. So this is when the entropy for higher DCFTs is universal. Any questions on this?
F is not, doesn't have some independent.
Yeah, very good question. It does not. Yeah, very good. F is just defined this way. It's the leading term in the free energy. And so, in fact, let me make some comments about that. Let me make some comments about this. So let's write down some comments. Because in some ways this is similar to the story in 2 dimensions, but there are some key differences. And one of them is that as Per pointed out. So, okay, the first comment I want to make is that in 2 dimensions, this series truncates. And there are a couple of ways of seeing that. One was the modular invariance argument we made earlier. But there's another way, which is just that in 2 dimensions, when you do this closed-at-kind reduction, you can't write down any additional terms. Right? The only term you can write down is the cosmological constant when you have some effective one-dimensional theory. So that's a very nice way of saying that to all orders in perturbation theory, the partition function at high temperature, or equivalently the Cartes formula, will be accurate to all orders in perturbation theory in theta or in delta. But in higher dimensions, that's no longer the case, and that's why there are these annoying dot that you have to worry about in higher dimensions, and there are infinite series of Wilson coefficients as opposed to a single number in 2 dimensions. So in 2, this is accurate non-perturbatively in delta, and be bigger than 2, infinite series of perturbative fractions. Okay. On the other hand, if you're only interested, if you allow a tolerance, if you say, okay, I'm okay with error of 1 over delta to the 17th power, then there's only a finite number of terms you can write down. And so there's a finite number of Wilson coefficients that you depend on. It could be very large, but it's fine. The second comment I want to make is related to Per's point. So in 2 dimensions, this single number C had many other interpretations, like Casimir energy and some TTOPE related to some anomalies. And there's also a homological C theorem, in fact. None of these things generalize to hierarchy. There's generally no RG monotonicity theorems or F, etc. In 2D there is, but in higher D there's not. There's no reason for there to be. And in fact, there are even examples of flows where it's known that this quantity F increases. So for example, Sachdev had one in the early 90s where you look at the 3D ON model and you flow to some n-1 free scalars, and you can actually show in the large n limit F increases by a factor of, I think, 5/4 or 6 bits or something like this. Well, there's another famous example too, actually, which was shown by Klebanov and Gaubser and Zeitlin and Pete maybe, which is this quantity F for this analogous quantity F in n equals 4 super Young Mills, as you go from the free point to the strongly coupled to larger tip coupling, F changes by a factor of 3/4. I think it goes down by a factor of 3/4. And this is a marginal deformation. Whereas if there was an RG theorem, if there was an RG monotonicity theorem, then under any marginal flow, this has to remain the same. So for example, like in 2 dimensions, whenever you have a conformal manifold and you deform, either from some supersymmetric marginal operator or from some JJ bar, this the central charge always stays the same. But this analog of the central charge, which controls the entropy, it can change. In fact, it does change. This is related to this kind of quote unquote famous 3/4 mismatch in black hole entropy in AS Vacuums as well. It's kind of funny actually, because I remember when I was in grad school, people would say this thing, and they would say like, oh, the central charge C is related to some count of the number of degrees of freedom in 2 dimensions. And they would say, well, there are two ways you can see this. One is that the C always decreases under RG flow, and the other is this C is like what shows up in the entropy in Cartes formula. And of course, these statements, they're both true. It's not like this is a wrong statement, but it's a little bit misleading because the fact that those are the same quantity in 2 dimensions does not, that's an accident in 2 dimensions. It doesn't generalize to like 4 dimensions, for example. Question. Okay, and the final thing I want to make, final comment I want to make before I get to some -1 to the j's, is that the regime of validity of the entropy is different, is qualitatively different. And D equals 2 versus D equals 2. So remember that for 2D CFTs, when you do this Cardi analysis from modular invariance, and then you find the saddle and so on, your calculation is trustworthy for the entropy as long as delta minus J is much bigger than the central charge. And I'll write the central charge as F here. So in 2 dimensions, this F is the same as C. But I'll write F just to make it just generalize. If you're not familiar with this, this is H and H bar. So maybe you recall that Hardy's formula, you need both H and H bar to be very, very large. This is the eigenvalues under L0 and L0. So you need the twist to be much larger than the number of degrees of freedom you have in 2 dimensions for Hardy's formula to be valid. And this is true for Eisenhower as well. This is nothing to do with quantum. Now, for d bigger than 2, what I just told you here is that you actually need a stricter condition. You don't need that the twist is much bigger than f. You need that the twist is much bigger than square root of f times delta, which in general is much larger, right? If you imagine f is some order 1 number and you go to very, very high energies, then you need this twist to be larger. If you don't obey this, then when you do the saddle point analysis of this to get here, you're not at a parametrically small beta, in which case you don't trust this, because all these dots can be just as large as the terms that you keep. So this is just a pure CFT statement. This has nothing to do with this is when the CFT is trustworthy. This has nothing to do with gravity, but there's a very, very interesting interpretation of this that I think is very deserves further exploration that I want to comment about for black holes. And to do this, I'll tell you a fact about black holes, about ADS curve black holes in greater than or equal to 4 dimensions, which is that if ADS curve black holes are spinning very, very quickly, they are unstable. In particular, they'll never dominate the canonical ensemble. So this was first mentioned, I think, in a paper by Cardozo and Diaz, like more than 20 years ago. But there was recently a lot of work by Shiraz Minwala and Sok Kim and that whole group in something you could in the past couple of years they're called gray galaxies. You can look at these papers. But roughly speaking, for curve ADS black holes in d bigger than 3. So here I use capital D because this is just this is a statement about general relativity, and I use capital D because of course if we want to use ADS CFT, this will be little d plus 1. So the condition for them to be stable and to dominate the canonical ensemble, they need the mass of the black hole or the energy to obey this. So this is some number. This is an order 1 number you can compute, and it slightly depends on the dimension. So I'm not going to write it, but because it depends if you're an ADS 4 or ADS 5. But always the right-hand side takes the same form. And the LADS to make up units. Okay, so what it's saying is that if you're too close to extremality, like if the mass minus the spin of the black hole, if the black hole is spinning really, really, really fast, then there's some instability, and there was recent discussion by Shiraz and friends about what this instability leads to. But let's just translate this to what the CFT data is. So the energy is like delta, J is like the spin, and this G Newton to the minus 1/2. This is like F. This is like F. Yeah, F to the positive 1/2. Right. Remember this F. There always will be some like Brown-Pinot type formulas where for holographic theory, it's just like the central charge for 2D CFTs. This is related to LADS over G Newton. These Fs will still be counting some number of degrees of freedom. They will still be related to LADS over G Newton, which is some appropriate powers. So
is instability even in pure gravity? Is there?
I'm sorry.
The instability, is it required matter, or is it even pure gravity?
I think even with matter, it can be unstable. But actually, I don't remember. Go ahead. Yeah.
No, it's a bit in pure gravity.
Oh, in pure gravity, that's I don't know, because pure gravity then it's unclear because there's nothing for it to decay into. I think they assume some matter. So yeah,
there's some theory to that.
Yeah, no, but it always takes this functional form. So if I translate this is some number times root f times 1000. But in ADS3, this doesn't occur, and for ADS3, for these black holes to be stable and also to dominate the canonical ensemble, they need to be bigger than just this F. There's some order 1 number which is important, and this is related to the difference between enigmatic black holes and large black holes in ADS3, but that's just some factor of 2. So maybe I'll just draw this little table because I think it's very, very tantalizing that this functional form and this functional form are exactly the same, and this functional form and this functional form are exactly the same. So in 2D, So now I'll do the CFT dimensions. So in 2D CFT, the Carty formula is always valid when delta minus J is much larger than C or F. And you can prove actually that if you make some assumption, which we can discuss afterwards, but if you make some assumption of sparseness of the theory, you can prove for modular invariance that there's an extended regime of validity for the entropy of all 2D CFTs at large C. So you can prove that this gets extended to some number C. And this has a very nice gravitational interpretation as this extended regime is precisely when black holes dominate. So some condition of holographic nature gives you this extended regime validity. So in hierarchy than 2 dimensions, we know from effective field theory that if you're parametrically much larger than this square root of F times delta, your entropy is completely universal. So I think it would be very interesting if we can put some assumption here, maybe sparseness, maybe some gap to the single trace higher spin sector, whatever, such that again, these two greater than signs become just one greater than sign, and there's some number that you can. Of course, to prove this, so this result was a paper by Tom Hartman, Chris Keller, and Evan Stoica. And here they use modular invariance to just prove a pure 2D CFT statement. They just prove that, if the 2D CFT has some sparseness properties, you can prove that there's some extended regime validity here. Obviously, we don't have modular invariance available here, so I don't know exactly how one would go about proving it. But it'd be very interesting if just from pure CFT arguments, you could prove that this effective field theory has some larger range of validity if you make some assumption that's weaker than like all of some assumption like HPPS or something like this that you can show that there's some extended regime of validity. This is kind of a bit of a speculative comment, but I think it's fine. Any questions or comments? Okay, so now maybe I'll now talk about what I promised to talk at the beginning of the talk. So here, this is the partition function that we've computed, and this is valid at high temperature and some order 1 chemical potential. So that means we do a small twist of the partition function. So now let's do a large twist and see what we get. So the question is, can we compute this object in CFT? So we computed this one so far. Okay, so we already computed this one at high temperature. This was what was given by this infinite series of Wilson coefficients. But now I want to ask, for example, suppose I include this -1 to the j. What is this guy in the limit of high temperature in order 1 angular chemical potential? So remember, in 2 dimensions, we did this using a more complicated modular transformation. We got a factor of 1/4. And now in higher dimensions, without this, we use some effective field theory techniques, and we got some universal answer in terms of some Wilson coefficients. So what I'll first do is I'll first rederive this answer in 2 dimensions, just using a path integral technique without using any modular invariance. So how would you compute this thing? Well, this thing is like computing the path integral on this cylinder, where as you go around this S1, let's say this S1 has length theta, and this is the other S1. As you go around this cycle, you do a 180-degree twist in your SD-1, which is just S1. Right? That's like the definition of what this is. So what this is saying is that as you go around this, you identify this leg with this leg with this leg, and of course this with this. So computing the path integral on this geometry is precisely what's computing this particular problem. And now I'm going to cut and glue. I'm going to put this guy on top of this guy and say what's it equivalent? This manifold is equivalent to the following. I put this guy on top of this guy. Now this guy is on the bottom, this guy's on the top. This guy is equivalent to himself. This guy is now equivalent to this. This is equivalent to this. And now this whole thing has length 2 beta. And now this is an S1 or SD-1 mod Z2. This was the S1 or SD-1. Now we cut it in half. And the Z2 action is just rotation by 180 degrees. So beta is very, very small here. And what's going on here? We can view this as some non-trivial S1 fibered over this SD-1 mod Z2. Right? It's a non-trivial vibration because as you go around once, you get flipped to this other side. So we'll discuss it in a second, but roughly speaking, what's the differences? The two differences, the volume of the SD minus one goes to half. You modify the Z2, and the beta gets doubled. And if you remember, the leading term for the free energy went as the volume of SD minus one over beta to the D minus one times 1 plus omega squared. This number F. So if this goes down by a factor of 2 and this gets doubled, then we get a factor of 1/2 overall and a 2 to the D minus 1, which overall gives a power of 2 to 1 over 2 to the D. Does this cartoon make sense? And now, actually, you can imagine if we put an arbitrary phase e to the 2 pi I p over qj, then you, instead of cutting this in half, you would cut into q pieces and you'd have to stack them in a more complicated way. And then this volume of SD minus 1 mod zq would go down by a factor of q, and you'd have to stack q guys on top of each other. So then the beta would get multiplied by q. So you get a factor of 1 over q to the d in general. Okay, this was a little bit fast. So let me say this again in a equivalent, but maybe a little bit more systematic way, which is let's view abstractly what is this manifold that we constructed and want to compute the path integral. So more abstractly, we want to compute the path integral on this geometry. So there's an S1 with inside 2 beta, and there's an SD minus 1, and we want to by overall ZQ, where the action of this ZQ is, suppose you have this n hat is some unit vector on your SD minus 1, and tau is the length of the S1. This action of the ZQ acts with some element R, such that R to the Q is equal to 1. So R could be this identity. So R could be like a rotation by pi degrees in this example over here. And tau goes to tau plus beta. So this is a non-trivial bundle, right? Because this ZQ acts on both of them. This is not equal to the product of SD minus 1 times S1 mod ZQ or S1 times SD minus 1 mod ZQ. But what we're going to do is in the beta goes to 0 limit, we're going to treat this as if the bundle were trivial. And we're going to treat this as this partition function. Because, so where would we get in trouble? If you're computing the integral of some locally gauge invariant terms, then it doesn't, then you don't know that you're on some non-trivial bundle. The only term that you will notice this would be these topological terms that Theo asked about. So indeed, actually, in theories with gravitational anomalies, this is a little bit too fast, and then we can discuss a little bit what happens there. But if in your effective action you just have like cosmological constant terms or Einstein terms or Maxwell terms, this will be accurate to all orders of perturbation. So integrals, local gauge invariant quantities. Don't realize. Non-trivial formation. And actually, so here I wrote the leading order effect, which is the power of 1 over q to the d. That came from the cosmological constant. But in fact, actually, you could compute corrections as well. So for example, the Maxwell term, that was a term that went as beta to the d minus 3. This will go down by power of 1 over q to the d. This will go down by power of 1 over q to the d minus 2, right, and so on. Right, so those terms still have this volume of SD minus 1, but now the beta power is different. So if beta gets changed to q beta, it'll go down by different power. And also, if there is a gravitational anomaly and there is some Chern-Simons-like term in the effective action, it'll still be subdominant compared to this. So if you're interested in the strict beta goes to infinity limit, the leading order term will still be this 1 over q to the d. Now the perturbative corrections could be more subtle. So one way they could be more subtle is these topological terms. There's one other way that they could be more subtle, which is this manifold is not so innocent. If d equals 2, this is fine. If d equals 2, then S1 mod ZQ is just an S1 where the size of the S1 just changes by a factor of q. But if d is bigger than 2, then this SD minus 1 mod ZQ can have fixed points. And so for example, one very simple one to visualize is imagine d is equal to 3. So now you have this S2 mod ZQ, and remember the action of this ZQ was to rotate by like 2 pi over q. Okay, so there are 2 fixed points. There's the north and the south pole. And in general, there'll be a codimension 2 surface of fixed points of this span. So let me write this here. Well, of course, it depends precisely what the action of this CQ is. If you do have an odd dimensional CFT, then there will always be some fixed point if you're just inserting some angles, because there's always, then this cartan, there's always one direction left over. But for an even dimensional CFT, if you're very clever with your choice, like you put -1 into the J1 and then some other angle into the J2, you could array that there are no fixed points, but generically there will be some fixed points. For example, S2 mod PQ has north and south pole. And when they're fixed points, that means that you can write down a defect action. The defects by themselves will again have their own effective action that you can write down. Now, fortunately, again, because these always have some non-trivial codimension, these defects will always be subleading, just from dimension analysis, to the cosmological constant. So it's still a true statement that in the high temperature limit, the leading order term of the partition function with this e to the 2 pi I p over q inserted is still the same partition function down by a factor of 1 over q to the d. However, if you're interested in perturbative corrections, then you may also have to worry about one is topological terms, and you may also have to worry about defects. But that's fine. I mean, they're not so scary. The only downside is, of course, they come with their own set of Wilson coefficients, and in principle, you have, these are new things you have to compute. So these are suppressed perturbatively, and they show up at order beta squared relative to leading. So I'll write down the expression that we can write down. So the log of base of e to the minus beta. So what is this going to equal to? The first term is the term that we discussed. This will be the original partition function down by a factor of 1 over q, coming from the fact that the volume of the sphere went down by a factor of q. And now you have the original partition function at q times beta. And then there are two additional terms you have to include. One is a topological term. So this will be if the theory has a gravitational anomaly. This doesn't always happen, but if the theory has a gravitational anomaly, like in 2D CFTs, if C left is not equal to C right, there will be a term here. And there will also be a defect term. I'm not going to write down the explicit expressions for this, but if you're interested, you can see that. You can see our paper where we write down some expressions, explicit expressions. But this is the general expression to all orders in perturbation theory of this partition function with this insertion of P over Q. Notice again that, of course, for this to be, if you want to use effective field theory here, now you need Q beta to be much less than 1. So if you put in some really crazy angle with some huge denominator, then you might need to go to extremely low temperature. It's an extremely high temperature for you to be able to explicitly see this. Maybe I'll make one comment about that, which is, you can ask, like, can you test this expression? And of course, you can look at this for free theories, but they're a little bit subtle because they have zero mode and you can compute things. But one thing we did for fun was we looked at like the 3D easing model. 3D easing model, now they're experts who have like bootstrapped like the first some handful of operators, and so they know like some like order, like I think operators up to order delta around like 12-ish. To some varying amounts of precision with various spins. So you can just like build this partition function yourself and plot it as a function of beta, and then insert one with a -1 to the j. And you can kind of see this factor of 1 over q to the d kind of emerge at this, although it's a little bit sketchy because you don't have that many operators, and the fact now that as you go to higher and higher temperature, you need to go at higher and higher energies, and people have only computed in the scaling dimensions up to so high. So this factor may be a little bit annoying if you're actually trying to like put this on a computer, but in principle it's something you could do. Okay, so any questions? This is kind of the main punchline. I have some more things to say, but this is like the main point. So if there are any questions, maybe now is a good time to take any. comment. Yeah, go ahead, Jungdi.
I hope for a quick question. So the geometry you try to compute does not really have this singularity. You have this.
That's right, that's right.
singularity because you try to pretend this.
That's right. Other questions? Okay, so maybe let me make a comment about fermionic theories now. So actually, so far I was just talking about bosonic CFTs, but for fermionic theories, the story is a little bit different and a little bit more subtle. And the reason, of course, is that for fermionic theories, if you ever have a fermionic theory, you need to do more than just specify the manifold. You also need to specify the spin structure. So that's just saying that if you have some cycle, like some S1, for example, you need to specify what the periodicity of the fermions is. And in 2 dimensions, there are 2 different periodicities you need to specify. You need to specify around the S1 in the time direction and the S1 in the space direction. But in higher dimensions, if you compute partition function like SD minus 1 times S1, you just need to specify the periodicity around the S1, which amounts to saying if you insert a -1 to the F or not in the partition function. And in general, for a non-supersymmetric theory, both of these insertions we assume will give some different set of Wilson coefficients that in principle have nothing to do with each other, except that obviously the ones with the -1 to the F will be smaller because the partition function will be less. So stuff like this around S1, and that corresponds to, are you computing trace of e to the minus beta h plus I omega j versus trace of e to the minus beta h plus I omega j times -1 to the F. Okay. And in general, there will be some set of Wilson coefficients like F, C1, C2, etc. for this theory, and some different set of Wilson coefficients I call F tilde, C1 tilde, C2 tilde for this theory. And in principle, these are independent guys that just have to be computed separately. Now you might worry. Now suppose I put in some arbitrary phase. So this -1 to the F, of course, this is also e to the 2 pi I j. Now you might worry if I put in some arbitrary e to the 2 pi I j times p over q, maybe there'll be an infinite, like yet more Wilson coefficients that you have to compute. But the answer is no. You can just do the stacking trick, and you'll always reduce to either this theory or this theory. Now, which theory you reduce to depends on how many times that every time you stack, you have to maybe the periodicity of your fermions may change, right? Like if you stack to antiperiodic ones, then they'll become periodic as you stack them. So if you go through this procedure, it depends on something like the periodicity, the parity of P plus Q. So P plus Q is even versus odd, then you get some different effective field theory. But you can always map some arbitrary fractional phase of this versus to this versus this. And those of you who've studied some 2D CFT may be familiar with this. You know that in general for 2D CFT, if you specify like the spin structure with like which now you need to specify both if you're in the NS or Ramon sector and this -1 to the F, you know that actually depending on which element of SL2Z you get in, you may map to either the Ramon sector or the NS sector. So the high energy behavior of this partition, high temperature behavior of this partition function versus this partition function will depend on will have different Wilson coefficients. And in 2 dimensions, this is a very, very nice interpretation. So in 2 dimensions, the difference between F tilde and F is precisely up to some factors of n2 pi, the ground state energy of the Ramon sector. So in 2 dimensions, if you insert some -1 to the F here versus here, this one is invariant, but this one gets transformed to the Ramon sector. So when you then take the high energy limit, you then don't get the vacuum, you don't get the NS vacuum, you get the NS vacuum shifted by the Ramon sector. So this is kind of nice because I think in some sense these new sets of Wilson coefficients are some kind of analog of a Ramon ground state energy for higher DCFTs. Because they're telling you the high temperature behavior of the partition function with this -1 to the F inserted versus without this -1 to the F inserted. But I think that's kind of a nice thing with these fermionic theories that you can I'm sorry, there's a squeezing right here. That you can have this interpretation done. I think this is most of what I wanted to say. I don't think anyone will complain if I end 5 minutes early, but I think I'll stop here and thanks very much for your attention.
How explicit can you make like the universality formulas?
Yeah, I think this is an exact equation to up to non-perturbative corrections.
But yeah,
Beta.
can you explain them from like vacuum dominant?
Oh, good question. From vacuum dominance, no, I don't think so, because usually to make these arguments work, you need some kind of modular transformation, and this vacuum dominance is the same that you make at low temperature, and these are all high temperature expressions. And of course in two dimensions, then we understand this expression exactly. So in two dimensions, you understand is that from vacuum dominance, this S defect doesn't exist. This S logical can still exist, and we can also explain this in two dimensions when there's a C left minus C right term. But in two dimensions, you can explain this exactly from vacuum dominance. But in higher dimensions, I only know from this EFT perspective. It's a little bit funny, actually. In some sense, this cutting and stacking method I did, it's kind of like doing a modular transformation in higher D. Like that's kind of what it is. But of course, you're using this effective field theory as opposed to the theory itself.
You look at the black holes in ADS, everything's just sort of trivially extend into those solutions. I mean, they're corresponding black holes.
Oh yeah, very good question. Yeah. Indeed. So there are black holes. Yeah, good. So in ADS3, of course, maybe you're talking about these SL2Z black holes like that. There's some solutions corresponding to. There's some saddles corresponding to these.
Yeah, in higher dimensions now.
Yeah, that's right. Yeah. So there's analogous theory you can make in higher dimensions. We wrote down some metrics. There's some subtleties that were a little confused, which I can maybe discuss with you afterwards. But it seems that there are solutions you can write down.
But they don't have like any fixed points, right? They're smooth.
I think they're smooth. I think they're smooth.
So what happens if you put the irrational number?
Oh, sure. Good. Okay. Yeah. Okay. Very good question. So you can ask what happens if you put you can ask what happens if you put like some number to the j, and this is e to the 2 pi I, like some j where times some square root of 2, something like this. Like what happens here. So this is still a perfectly well-defined function. Like there's nothing stopping you from defining this. And you can ask how does this behave when beta is very, very small? You'll get this fractal-like pattern. So this is how it behaves. So any real number, like any irrational number, there's always this continued fraction approximation of this number. So there's a series of rational numbers that approximate this number. So the square root of 2 is it's like some number over a over b plus c over d plus whatever, and truncating this series gives you better and better, kind of the best rational approximations to this. And whenever you truncate this, you'll get a sequence of rational numbers with larger and larger denominators. So as beta becomes smaller and smaller, then what'll happen is like the beta that's closest to that hasn't yet if beta is like 1 over 100, then you take the largest rational number whose denominator is less than 100. You see what I'm saying? So it's like you take the number such that beta hasn't realized that this square root of 2 is not yet rational, and it'll behave this way. So if you like plot this function as a function as beta gets smaller and smaller, you'll get these kind of regime changes, and you'll get this kind of fractal-like structure. And the exact same thing happens if you plot a modular form at real part of tau that's irrational. You can take like Dedekind eta function or something and plot it for some irrational real part of tau, and you'll get this fractal-like structure. And we think the same thing will happen in higher D for this reason. But indeed, the precise statement is that like if you put an irrational angle here and you take the beta to 0 limit, there's not really a well-defined limit like there is for a rational number. For a rational number, it'll diverge with a specific prefactor. But if you put an irrational number, as beta gets smaller and smaller, this prefactor will change and it'll keep decreasing as beta goes down.
All right, let's thank Nathan again.
Thanks.